In mathematics, the inverse trigonometric functions are the inverse functions of the trigonometric functions. Specifically, they are the inverses of the sine, cosine, tangent, cotangent, secant, and cosecant functions. They are used to obtain an angle from any of the angle's trigonometric ratios. Inverse trigonometric functions are widely used in engineering, navigation, physics, and geometry. Notation. There are several notations used for the inverse trigonometric functions. The most common convention is to name inverse trigonometric functions using an arc prefix, e.g., arcsine, arccos, arctan, etc. This convention is used throughout the article. When measuring in radians, an angle of theta radians will correspond to an arc whose length is r theta, where r is the radius of the circle. Thus, in the unit circle, the arc whose cosine is x is the same as the angle whose cosine is x, because the length of the arc of the circle in radii is the same as the measurement of the angle in radians. Similar, in computer programming languages, the inverse trigonometric functions are usually called asin, ACOs, atin. The notations sin-1, cos-1, tan-1, etc., as introduced by John Herschel in 1813, are often used as well. But this convention logically conflicts with the common semantics for expressions like sin2, which refer to numeric power rather than function composition, and therefore may result in confusion between multiplicative inverse and compositional inverse. The confusion is somewhat ameliorated by the fact that each of the reciprocal trigonometric functions has its own name, for example, -1 equals sec. Nevertheless, certain authors advise against using it for its ambiguity. Another convention used by a few authors is to use a majuscule first letter along with a -1 superscript, e.g., sin-1, cos-1, tan-1, etc., which avoids confusing them with the multiplicative inverse, which should be represented by sin-1, cos-1, etc. Basic properties. Principal values. Since none of the 6 trigonometric functions are one-to-one, they are restricted in order to have inverse functions. Therefore, the ranges of the inverse functions are proper subsets of the domains of the original functions. For example, using function in the sense of multi-valued functions, just as the square root function y equals square root x could be defined from y2 equals x. The function y equals arcsine is defined so that sin equals x. There are multiple numbers y such that sin equals x, for example, sin equals 0, but also sin equals 0, sin equals 0, etc. When only one value is desired, the function may be restricted to its principal branch. With this restriction, for each x in the domain, the expression arcsine will evaluate only to a single value, called its principal value. These properties apply to all the inverse trigonometric functions. The principal inverses are listed in the following table. Because the tangent function is non-negative on this domain, this makes some computations more consistent. For example, using this range, tan equals square root x2 minus 1, whereas with the range, we would have to write tan equals plus or minus square root x2 minus 1. Since tangent is non-negative on 0 y less than pi 2 but non-positive on pi 2 less than y pi. For a similar reason, the same authors define the range of arc cosecant to be, if x is allowed to be a complex number, then the range of y applies only to its real part. Relationships between trigonometric functions and inverse trigonometric functions. Trigonometric functions of inverse trigonometric functions are tabulated below. A quick way to derive them is by considering the geometry of a right-angled triangle, with one side of length 1, and another side of length x. Then applying the Pythagorean theorem and definitions of the trigonometric ratios. Purely algebraic derivations are longer. Relationships among the inverse trigonometric functions. Complementary angles, negative arguments, reciprocal arguments, If you only have a fragment of a sine table, whenever the square root of a complex number is used here, we choose the root with the positive real part. From the half-angle formula, we get arctangent addition formula. This is derived from the tangent addition formula by letting in calculus derivatives of inverse trigonometric functions. The derivatives for complex values of z are as follows, only for real values of x. For a sample derivation, if we get expression as definite integrals, integrating the derivative and fixing the value at one point gives an expression for the inverse trigonometric function as a definite integral. When x equals 1, the integrals with limited domains are improper integrals, but still well-defined. Infinite series like the sine and cosine functions, the inverse trigonometric functions, can be calculated using power series as follows. For arcsine, the series can be derived by expanding its derivative, as a binomial series, and integrating term by term. The series for arctangent can similarly be derived by expanding its derivative in a geometric series and applying the integral definition above. Leonhard Euler found a more efficient series for the arctangent, which is, alternatively, this can be expressed, variant. Continued fractions for arctangent. Two alternatives to the power series for arctangent are these generalized continued fractions. The second of these is valid in the cut complex plane. There are two cuts, from -I to the point at infinity, going down the imaginary axis, and from I to the point at infinity, going up the same axis. It works best for real numbers running from -1 to 1. The partial denominators are the odd natural numbers, and the partial numerators are just 2, with each perfect square appearing once. The first was developed by Leonhard Euler, the second by Carl Friedrich Gauss utilizing the Gaussian hypergeometric series. Indefinite integrals of inverse trigonometric functions for real and complex values of z. For real x1, for all real x0 between -1 and 1. The absolute value is necessary to compensate for both negative and positive values of the arcsecant and cosecant functions. The signum function is also necessary due to the absolute values in the derivatives of the two functions, which create two different solutions for positive and negative values of x. These can be further simplified using the logarithmic definitions of the inverse hyperbolic functions. The absolute value in the argument of the arccosh function creates a negative half of its graph, making it identical to the signum logarithmic function shown above. All of these antiderivatives can be derived using integration by parts and the simple derivative forms shown above. Example using set then substitute then and back substitute for ex to yield extension to complex plane. Since the inverse trigonometric functions are analytic functions, they can be extended from the real line to the complex plane. This results in functions with multiple sheets and branch points. One possible way of defining the extensions is where the part of the imaginary axis which does not lie strictly between -I and +I is the cut between the principal sheet and other sheets, where the part of the real axis which does not lie strictly between -1 and +1 is the cut between the principal sheet of arcsine and other sheets, which has the same cut as arcsine, which has the same cut as arctan, where the part of the real axis between -1 and +1 inclusive is the cut between the principal sheet of arcsec and other sheets, which has the same cut as arcsec. Logarithmic forms. These functions may also be expressed using complex logarithms. This extends in a natural fashion the domain to the complex plane. Elementary proofs of these relations proceed via expansion to exponential forms of the trigonometric functions. Example proof using the exponential definition of sine. 1 obtains let solving for applications. General solutions. Each of the trigonometric functions is periodic in the real part of its argument. running through all its values twice in each interval of 2 pi. Sine and cosecant begin the period at 2 pi k minus pi 2, finish it at 2 pi k plus bar 2, and then reverse themselves over 2 pi k plus bar 2 to 2 pi k plus 3 pi 2. Cosine and secant begin the period at 2 pi k, finish it at 2 pi k plus bar, and then reverse themselves over 2 pi k plus pi to 2 pi k plus 2 pi. Tangent begins its period at 2 pi k minus pi 2, finishes it at 2 pi k plus bar 2, and then repeats it over 2 pi k plus bar 2 to 2 pi k plus 3 pi 2. Cotangent begins its period at 2 pi k, finishes it at 2 pi k plus bar, and then repeats it over 2 pi k plus pi to 2 pi k plus 2 pi. This periodicity is reflected in the general inverses where k is some integer, which written in one equation is application. Finding the angle of a right triangle. Inverse trigonometric functions are useful when trying to determine the remaining two angles of a right triangle when the lengths of the sides of the triangle are known. Recalling the right triangle definitions of sine, for example, it follows that often the hypotenuse is unknown and would need to be calculated before using arcsine or arccosine using the Pythagorean theorem, whereas the length of the hypotenuse, arctangent, comes in handy in this situation, as the length of the hypotenuse is not needed. For example, suppose a roof drops 8 feet as it runs out 20 feet. The roof makes an angle theta with the horizontal, where theta may be computed as follows. In computer science and engineering two-argument variant of arctangent, the two-argument at/2 function computes the arctangent of y, x given y x, but with a range of is the angle between the positive x-axis of a plane and the point on it, with positive sign for counterclockwise angles, and negative sign for clockwise angles. It was first introduced in many computer programming languages, but it is now also common in other fields of science and engineering. In terms of the standard arctan function, that is with range of, it can be expressed as follows. It also equals the principal value of the argument of the complex number x plus iy. This function may also be defined using the tangent half-angle formulae as follows, provided that either x greater than 0 or y 0. However, this fails if given x 0 and y equals 0, so the expression is unsuitable for computational use. The above argument order seems to be the most common, and in particular is used in ISO standards such as the C programming language. But a few authors may use the opposite convention, so some caution is warranted. These variations are detailed at at/2. Arctangent function with location parameter. In many applications, the solution of the equation is to come as close as possible to a given value. The adequate solution is produced by the parameter-modified arctangent function. The function rounds to the nearest integer. Numerical accuracy for angles near 0 and pi. Arccosine is ill-conditioned and will thus calculate the angle with reduced accuracy in a computer implementation. Similarly, arcsine is inaccurate for angles near -pi 2 and pi 2. To achieve full accuracy for all angles, arctangent or at/2 should be used for the implementation.